today at distance, speed, and velocity. This is a look at how the various kinematic variables relate and how we look at them in terms of graphical and some beginning mathematical relationships. Little inspiring quote from Einstein. So starting with this graph right here, position time graph, we've got some curves on it, a moving object. So I want you to take a second, maybe pause the video, and figure out which of the four graphs below represent the velocity time graph for that one. And we'll come back and talk about this at the end. Okay, moving on. When it comes to kinematics, we're talking about the description of motion. And we're going to start really simply with one-dimensional motion, like that bowling ball along the straight line down there. And then we'll look at more complex motion, two-dimensional, something in a parabola, that kind of thing. We will talk about more dimensions as well, but we won't get into that in a lot of detail because two-dimensional is plenty for most of what we're thinking about. Specifically today, we're going to look at kinematics variables and one-dimensional motion graphs, displacement and velocity as our two key ideas, and draw those graphs. So when it comes to kinematics variables, we have the following. We have time, which is measured in seconds, position, which is measured in meters, that's a vector symbol above it, displacement, which is essentially a change in position, which is also a vector in meters, distance is sort of a subset of that. And then we have velocity measured in meters per second. And that's a vector as well, has direction. And then finally, we're talking about with its subset speed, its magnitude, and then acceleration, meters per second squared. We'll get more into acceleration next time. So right now we're talking about the first few of these, and next time we'll talk about acceleration. It's kind of our look. So as an example of this, we'll start with, imagine, if you would, a trip to school. So there's a house, there's the school, very simple pictures, and we are going to start at the house and end up at school. And this little dotted line is our path we're going to take. So whenever we talk about kinematics, we always need to define our starting point or origin, which we can label as position 0. In this case, it's one-dimensional, so it'll be along a line. Then we wanted to define a coordinate axis. So moving to the right, we're going to call our positive x direction. And we'll mark out 100, 200, 300, 400 meters as we go. And then we need our reference frame. And so our reference frame is us standing still looking at this. We're not moving with the person walking to school or traveling to school. We are in the frame of the ground, the home, the school. So for the whole trip, we could ask some questions. What is the total distance traveled? Well, that's, if you think about a step counter, how many total steps did you go? So we went 100 meters, 200, 300, then we went back 100, so that's add another, and then we went forward 200 meters for a total of 600 meters traveled. Now, on the other hand, we could talk about displacement, and displacement is your change in position. If you start at home at 0 meters and you end up at a position 400 meters away in the positive direction, your displacement is positive 400 meters, right? So that delta x. Notice that our displacement is a smaller number than our total distance traveled because we care about direction or how far we've traveled from our starting point. We can do this for small segments. So if you think about the section where you go from B to C and back to C, the distance traveled is 200 meters, 100 meters from B to C and 100 meters back. But for displacement, that is only going to be positive 200 meters of displacement, and then negative 200 meters of displacement means our total displacement is 0 for that segment. If we talk about just from C to B, the distance is 100 meters, but the displacement is negative 100 meters. Right? Whenever we're dealing with vectors, the sign in this case is indicating direction. Because it's a one-dimensional motion, positive can be one direction and negative can be the other. So to kind of recap all of this, the distance is the total ground you cover in any direction. Displacement is the change in position. And it has direction information because it's a vector. For one-dimensional motion, positive and negative is enough to specify direction. But you could also choose to say forward, backward, north, south, that kind of thing, left, right. But positive and negative is usually what we use. And for 2D motion, we have to use a more formalized vector. So if we were to imagine that every 10 seconds we get to another one of these tick marks, so in other words, to go from 0 to 100 takes 10 seconds, we can start talking about speeds and velocities. For the whole trip, the average speed is going to be the distance traveled divided by time. That was 600 meters divided by the 60 seconds it took for an average speed of 10 meters per second. This is like the speedometer in a vehicle that's telling you how fast you're traveling. Or in this case, it's the average. So if you took the total distance traveled and divide by the total amount of time. This is kind of looking at maybe Google Maps telling you about your total journey. The average velocity is going to be different because the velocity depends on the displacement divided by time. And you only traveled positive 400 meters in that 60 seconds. So your average velocity is positive towards school in this case, but only 6.7 meters per second. That's because you went backward for a time and retraced your steps. From B to C, we could do the same thing. The average speed is still 10 meters per second, but the average velocity is 0 meters per second because you have covered no ground, right, in total. You've covered ground, but you haven't gone anywhere away from your starting point from B to C. You're in the same place you began. From C back to B, the average speed is still 10 meters per second, and your average velocity is now negative because you're heading in the negative direction. So, kind of to put that all together, average speed is distance over time. Average velocity is displacement over time, and velocity here is a vector because displacement is a vector. It gives you direction information. Average velocity is not actually used all that often because of these things like you end up with 0 if you do your average velocity for a whole day. From when you wake up in bed until you fall asleep in bed, you've traveled no distance away from the origin or no displacement during your day. So let's look at instantaneous velocity, which is how fast you're moving in a direction at a given moment, and a graph. So if you have your packets, access to them, you can look at these. If you don't have them yet, this is posted for you on Classroom. But there's a bunch of different position time graphs, and we're trying to figure out what the velocity time graphs look like. And so you can say, well, if we've got a particular distance traveled in a particular time, right, you're really looking at the slope of this graph to find that. And that tells you that for 3, you're going 2 meters in 2 seconds. So that's going to be, 4 meters in 2 seconds. So that's going to be a speed of, 2 meters per second if we write it there. And that's for number 3. And you can go through and do this for all of these graphs and give yourself kind of a look at them. Erase that for us. You can also do that for some more complicated things. This is an example of a trip again, making a graph. Just remember the displacement is up here and the delta t is horizontal. So when we talk about average versus instantaneous velocity, the average is the total displacement over time, but the instantaneous is actually the amount you've traveled displacement-wise over a very short time interval. In other words, the limit as that time interval shrinks to 0. This is essentially a derivative, but it can be seen as the slope of the line or the slope of a tangent line. And so here's an example of that, right? This is really a derivative, and we haven't really gotten into this in depth, but if you could draw a tangent line at the point you care about, then that's what we would be talking about. So if we go back to our original question, right? If we look at the different segments, this last segment, we show something going from very steep to less steep. And so that means it's slowing down, right? Because the slope is getting more towards 0. In the middle, we have a constant slope, which indicates a constant velocity. And at that beginning section, we have a place where it's getting steeper, which means it's speeding up. So if we look at these 4 graphs, there's only one of them that shows speeding up at the beginning, constant velocity in the middle, and then slowing down at the end, and that is letter D. All right, so the practice graphs that I showed you, plus some additional ones, are pages 8 through 13 in the packet. If you want some additional reading and you already have your Halliday book, which I'll refer to as HRW from now on. This is the physical textbook, not the digital one I posted. That's pages 8 through 13. In the packet, and chapter 2, section 1 through 5 in that book.